let's see. Okay, sorry. Where we were at last time, and I grabbed the wrong pen, is I introduced the Boltzmann. I should just throw this away. That would be much smarter, wouldn't it? I introduced the Boltzmann Formula, which is KBLN number of microstates. The symbol for that tends to change depending whether you're a physicist or a chemist or a biochemist, apparently. I just wanted to show you that I did one thing that was really kind of manipulative. I showed you a brief derivation of this, and I did that by showing you the Gibbs entropy formula, which is this. And I just want to remind you that I started here, and we talked about probability of state. Of course, we often use pegs in a chess piece on a chessboard. How many places does the chess piece have? Yada, yada, yada. Maybe there's 2 chess pieces anyway, or X is on a circle. And I showed you how we could go from here to here. And I do that for my undergrads, but let me tell you what's going on. So I don't think that this, the Boltzmann formula, I don't think there's a derivation for it. It just is. Now, I could be wrong about that. I meant to look it up before class, but I don't know if something happened right before class. And so I didn't have time to see. I looked before, and I just don't think there's a derivation. The guy just said, hey, this is what it is. But notice I gave you a derivation from here to here. Or did I? All right? No, because then where did this come from? Where did Gibbs' formula come from, right? So I'm kind of doing that to you on purpose. I tricked you. I have actually tricked you twice last time. Where did that formula come from, right? If you're deriving things, where did the things we start with come from? Like a child says, why, and until you stop, right? So I did that to get you to kind of like accept this, because this is kind of a difficult thing to accept. And so I did this basically a fake derivation to get you here to say, oh yeah, I've seen that derived. Yeah, that's right. And no, I didn't, in the sense that if A is equal to B, then ln A is equal to ln B. That's the derivation I did, and that's not, I don't think that really counts. Anyway, just saying, I just wanted to point that out. But it's something I do to undergrads to try to make them comfortable with this. And I did something else to you. When we talk about number of microstates, we always start with chess pieces on a chessboard, but that's not remotely real. I mean, the entropy of a chess piece is, I don't know, was it made of polypropylene? What's the entropy per mole? What's the mass of the chess, right? That's the real entropy. These are nice little problems because they're easy to solve, but they're not real. Okay, so to get you to be okay with that, I said for a gas that you could say the number of microstates is this. Volume, I just kind of made that up, and then of course particles are indistinguishable. You'll always see a divided by n factorial. And I showed you that in this case we can take the derivative of entropy with respect to volume, get R over V. I showed you that. Let me write this down. S is KB ln v to the n over v over n factorial. Okay, so this is also wrong. This is flat out wrong. It's actually a mistake that's engineered to give you, this is correct, but this is not correct. This is not correct, but it does happen to give you the correct derivative. It's an engineered mistake. So, and I did it on purpose. Now, again, I did it to make you understand that we can get these things into forms that make sense, that are not chess pieces on a chessboard, because again, that's nothing. That is a piece of plastic. But I can turn this into things that actually make chemical sense. And then we can do derivations and get things that we know to be true. It's just that it's not true that this is not true. Now, I did that again to make you comfortable, but let me point out why this is wrong. And this is actually a substantial fundamental that all physical chemists, there's some of you analytical, yeah, anyway. I mean, you should know it no matter what, right? Analytical or not. And so the point is, the way I know that this is always wrong, and the kind of thing that makes me comfortable when I'm going to talks with a bunch of equations, and normally, you know, I'm kind of mathematical, but sometimes this can get, you know, if this stuff shoots over my head, then I get lost. I'm like, whatever. But I can kind of follow along even when I see a talk that's equation heavy, because there's certain little things that I can spot in the equations that make me comfortable. Last time I told you, if I see natural logs, I know that that's entropy. So if I can see that, I'm more comfortable and I can follow along better. Psychological, right? The other thing is, I told you, if I see Planck's constant, that's quantum mechanical. Again, I'm a little bit more comfortable. But the rule I violate here is one of units. This has a natural log, and the argument of the natural log has units. Is there a problem with that? Given I just told you there was? Yes? Guess what it is? Let me give you another example, because I actually know this one a little bit better at heart. Okay, e to the minus energy. Oh, I won't use e. Let me use the letter u, because we know what u is. Anything wrong with that? It violates the same principle. It's just I know this one a little bit better. Anyone have an idea what's wrong with that? That you cannot do this either. If you have an equation that's supposed to correspond to reality that employs the laws of physics and chemistry, if I see this, then it's wrong. The reason is, expand it as a Taylor series, right? One, minus, okay, yeah, I'm kind of blank. Minus u, is that right?
Yes, by 1 factorial.
Plus
U squared by 2 factorial.
Over 2, right?
Yeah.
Then it'd be minus u cubed over 6,
yeah.
Is that right? Yeah. Okay, what are the units of the number 1?
Nothing.
No units. Joules? Joules squared, joules cubed?
Yeah.
You can't do that. You cannot have any equation. I don't care for what. I don't care if it's the entropy of my cat. You cannot have a sum where the individual members have different units. You cannot do that. You cannot have an equation that makes sense that's tension plus time. You know what? The entropy of this cat is a kilogram plus a second. Huh? No, you can't do that. So this violates that. Natural logs can be expanded as a Taylor series too. So it's the same problem. I just don't quite remember offhand what it is. Okay, you do that. Guess what? Not only are you measuring energy against nature's thermal energy yardstick, you also wipe out the units. So exponentials, arguments of exponentials, and natural logs cannot have units. And I sometimes I will spot people doing that, and it's kind of stupid. Anyway, maybe I should work for the NSF. And maybe that's why they reject my article, because I say stuff like that on monkey. Anyway. All right, now, it turns out, now again, I lied to you. I always show this to my undergrads because, again, I want them, all right, we start here. Sorry. Again, sorry, bad day. They start here, I derive it, make them feel comfortable, not that it's a real derivation. They'll do homeworks that are easy to follow but not real, and then I'll do it. I'll actually show them this to make them think that, okay, it's real, but again, engineered mistake. Now, for undergrads, I'll stop there because then we go into grad school, which is what we're doing now. In terms of statistical mechanics, this is for a perfect gas. There are ways to analyze the number of microstates for a perfect gas. It's one of the harder problems. It's actually one of the ways to derive PV equals nRT. It's on, if you Google it, you can find it on Wikipedia, along with old NSF program guides. But Tillman's bitter. So you can find a correct statistical mechanical description of a perfect gas. It's kind of hard, so maybe we'll do that at the very end, but it's not this. Again, engineered to give you the correct answer. Okay, okay, so where am I at? What we're going to do today, here, I'll just wipe this out because this is just correcting some funny things. I don't know if I should do that, you know, like I say, I like making you comfortable with this stuff, but I also don't like lying, and that's why I'm telling you what I did. Maybe I shouldn't do it at all. Anyway. Okay, now let me tell you what we're going to start on today and for the rest of this time. which is, okay, let's say G, oh no, we're not going to really work with G, right? Remember that? I told you we're not going to do much with G. A is G, just at constant volume, and A and G really aren't that different, only for reactions producing or consuming gases, and most of the time we're not really too worried about that. Okay, so A is U minus TS, and therefore A minus U divided by T is equal to S. Okay, so a lot of the derivations we're going to do, then do this. Okay. All right, notice that when I do that, and I told you I wouldn't do this, but I'm going to do it anyway. I can do that. So what we're going to end up doing is we can build a lot of relationships, and I'll show you some neat ones today. Maybe a really neat one today, or maybe they'll spill over till tomorrow. So I can build relationships between things, but you're not going to see entropy there. So the letter S will magically disappear, but so what? It comes about from entropy. Again, entropy is just going to kind of hide itself. So expect that quite a bit. I'm also going to be using a lot of new a lot of new symbology today as well. Okay, with that said, I don't really care about this, so let me wipe this out. Let me see if, wow, this, look at that. Let me point out, I'm going to kind of do this again. Again, sorry, I'm a little bit just so flummoxed today that, okay. Okay, so starting again with this guy, and you don't need to write that down because you already did. Okay, let's start with what we already know, which is how internal energy is TdS minus PdV. Sorry, minus PdV. Okay, now maybe don't write this down, but in mathematics, this is technically what you call a first order homogeneous function. More importantly, all the partials are size extensive. So calculus on things that are real are a little bit different than normal calculus. So first order homogeneous, and these are extensive. Now that means that I can integrate them. That's what I'm trying to point out. I mean, ultimately, letters are letters and they can be integrated. You're used to calculus with x's and y's that don't mean anything. But when it comes to things that are real, it does introduce a difference. And if I'm teaching StatMech like to a normal class, I would actually spend the entire day on that, but we don't really have that luxury. I want to point out that, so I can integrate them. And I can integrate them in such a way that it corresponds to something I tell my class. I can turn mathematical expressions into actions, because these are things that are real. And in the case of the first order homogeneous thing, where the partials are size extensive, I can do this integral as though I'm filling a hole. Again, actions, right? I am going to not have a hole, I'll have a container and it's empty, so it's a vacuum, and I'll add gas. Okay, the initial state would be 0, so I'm going to integrate du, and of course I'll integrate the stuff on the other side. The box is empty, it's a vacuum, so the internal energy is 0. There's nothing in there, nothing has no energy. It sounds funny, but it's also true. Now the final state will be the internal energy. And I can know what that is. If it's argon gas, then it's 3/2. I'll add a mole, so it's 3/2 RT. Yeah, 3/2 RT. It's 3 degrees of freedom. If I toss in a mole, then it's 3/2 RT is the amount of internal energy. Now I'll just call that. Okay, and then I will integrate the entropy, and I will integrate the volume. And again, all of these, the volume is, I don't know, it's a meter cubed, and the entropy, again, I'll look it up. I can find the entropy of argon on the data table. So it'll be at STP. So I know what this is. It's so many, it's 100 joules per Kelvin. I don't know, it's something like that. Okay, whatever. So then I get U is equal to TS minus PT. Okay, so there you go. Okay, so what? Now, as I pointed out before, I can then isolate S. Sorry. I'm going to do this in kind of a funky way. I'm going to write this out in a little bit of a funky way. There we go. Okay, and another thing I'm going to do is I'm going to divide by KD. So divide by KD. This is not very symmetric. There I am erasing my writing again. Sorry about that. There we go. Okay, so hopefully you recognize this. So I still got S over KB. You recognize this. Anyone know what the symbol is for 1 over KBT? No, it's just called beta. It's just a symbol, beta. Beta U plus beta PB. Okay, again, symbology. You will see in any modern physical chemistry seminar, beta. It's 1 over KT. The reason that we have the symbol for this is kind of like H bar. You know, you have H Planck's constant, H bar, which is 2 pi, Planck's constant over 2 pi. It's the difference between angular frequency and frequency. It turns out we like to use frequency, but nature uses angular frequency, which gives us a factor of 2 pi. Quantum mechanical expressions would have 2 pi's every freaking where. It's so annoying that we just defined a new constant to absorb all those 2 pi's. Anyway, so beta is 1 over KBT. So you will see beta in absolutely everything, and no one will tell you what it is. That's what it is. You're kind of expected to know that from here on out. And anyway, it's kind of the thing you see in seminars, but no one explains it. You're part of the club. I guess that's what I'm trying to say. You're part of the club if you know what that is. And of course, you know that this happens to be minus beta A, right? Mm-hmm. You do? How? From no, those aren't the same. So folks, let me point out that I just threw this at you. I just threw this at you. I haven't proved it yet. I'm just kind of messing with you people. All right. So where does that come from? Let's see. What do I want to do? Wait, because I did something wrong. What did I do wrong? Again, sorry, I'm just out of it so badly today. Sorry. There was one, I'm missing a step. Sorry about that. Over here. Minus beta U. Okay, so I just took this thing and just brought over minus beta U, and this is minus beta A. Okay. All right, so what's going on is there's actually a couple ways to think about this. Let's look here. This is a bit of an aside. Now, I've got to do 2 things. For one, I've got to prove this. I haven't proved this yet. I'll do that in a second. But let me tell you a little bit more about this rearrangement. Right now, I've just done middle school level algebra. There's actually something way more significant to that than you realize. And so let me do ds is du over t plus p over t db. Right? Did I do that right? Yeah, okay. So what are the natural variables of S? Remember we did this with U, and we said that U's natural variables were S and V. So if I just put S on the other side, what are S's natural variables?
U and P.
Remember how this game works? It's like ridiculously simple. I think my cats could answer this question. U and V, right? The partials. Right. So the change in this is depending upon the change in that and the change in that. So that makes U and V the natural variables. Now, what are the conjugates then? So if U is a natural variable of entropy, then what's the conjugate of U? Now remember, the name of the game is, it's right in your face. Is it temperature? You're very close. You're thinking along the right directions, but you just got it wrong. Okay, hold on.
1 over t.
1 over t. It's 1 over t. It's a little funky. The conjugate of u is 1 over t in the world of entropy. Okay, the conjugate of v, v over t. V over t. Okay. Okay, now remember I said if you want to take a function and get rid of its natural variable, its dependence on a natural variable, you multiply it by the natural variable. Take the function, subtract its natural variable times its what? And the conjugate of u is? What is this? Now remember, this is a Legendre transform. What is this?
1 over t.
Yes, this is the same thing. This is actually a Legendre transform. You see this? Now again, let's recap, because I kind of threw a lot at you. Okay. We start here. Now remember, you learned this as junior or seniors in undergrad. It's not hard. Internal energy is heat and work. Minus sign, whatever. Okay, I told you that you can integrate these suckers because they're size extensive. I can fill a hole, and that's the same thing. I'm pretty sure I can. Okay, then left with u is Ts minus Pv. And from there, I do some algebra to this, with beta being 1 over kBt. That's all I did. What I'm pointing out to you is that I manipulated this into the form of a Legendre transform. This is entropy. It's just a new entropy. Just as enthalpy is a new form of u with different natural variables, this is a new form of entropy with different natural variables. Entropy, our buddy that looks like this, has natural variables of internal energy and volume. That's great. But I want to work with a guy that has natural variables of temperature. And so I Legendre transform away the dependence on internal energy and I put it on temperature. Technically 1 over temperature, that's a little bit of a detail that doesn't really matter. It's a little funky. So again, this is actually a new form of entropy. It doesn't have a name. I've always been annoyed at that. When I Legendre transform internal energy and I get rid of the entropy dependence, I get A, and that has a name, Helmholtz energy. If I Legendre transform away volume dependence on U, I get enthalpy, it has a name. If I Legendre transform both of them away, they're Gibbs energy, it has a name. When I do the same thing with entropy, they don't have names. I don't know why. But anyway, that's what this is. This is entropy, it just has different natural variables. It has a natural variable of volume, but not internal energy. It's temperature. 1 over temperature, detail, not a big deal. Okay, so I just wanted to point out that what this really was. Okay, so what? Let's see, where am I at? Okay. Now, I told you that I then have to prove where the heck this came from. Okay, and I'll do that from here. A is U, and yeah, I was just talking about this, right? Entropy, internal energy has a dependence on S. I don't like that. I want to put it on temperature, so I subtract the variable I don't like times its conjugate. And the conjugate's positive, so minus Ts. Okay, so then let's divide by kBt. Again, betas are going to be everywhere. I will write them out explicitly so that it's not like too mind-bending. Let's see here. Okay, then what have I got? Okay, then I've got, therefore, I'm just doing some algebra. S over KB minus U over KBT is minus A. Yeah, I basically, all right, so S has a minus sign, so I technically multiplied everything by minus 1. Okay. And so therefore S over KB minus beta U is minus beta A. Oh, and that's right up here. S over KB minus beta U is minus beta A. And it was also equal to beta PV, and that was actually from here. So, yeah, this gets really kind of convoluted. And hopefully it's not a little, you're not getting too cross-eyed. None of this is actually all that terribly important. I'm just playing some algebra games. The important thing is that the important thing I want to get across to you right now is that there are other forms of entropy than entropy. I can Legendre transform on entropy just like I could on energy, and I will do so quite frequently. And I will do so to solve problems in the most convenient form. That's a foreshadow. Okay, now so what? Okay, now it turns out that I am going to do quite a bit with this. All right, let's not worry about beta PV. I'm going to do quite a bit with this right now. And I'll write that again because it's terribly important. S over KBT. S over KB minus beta U is minus beta A. Okay, now I'm going to do something kind of funky here. I am going to say minus beta A is the natural log of a thing that I will call Q. Now, right now, you should be looking at me and saying, huh? Good, because this is out of nowhere. I have just decided that minus beta A is going to be the natural log of a thing I will call Q. Why not? Now, I can now solve for Q. Great. Q is going to turn into something very important. That's why I'm doing this. Right now, you should not, oh, I know what Q is. No, you don't. Or you do. Hey, what are you doing in here? You should have your degree by now. Okay, so now what is Q? So to do this, let me see here. Where am I at? Okay. Okay, let me do S over KBT. KB is natural log of the number of microstates. Okay, so I'm using Boltzmann's formula. Remember, I told you I was going to do this, right? I'm going to insert Boltzmann's formula. And now I'm going to just remind you, so S over KB minus beta U is natural log of the number of microstates minus, now I'm going to go ahead and start doing some derivations, natural log of e to the beta U. Of course, natural log of e to the x is x. So, I did the algebraic equivalent of multiplying by 1. Taking the natural log of e to something I did nothing. However, what I can do with this is that there is a formula for natural logs. ln A minus ln B is ln A over B. 1 over ln 1 over B is ln B to the minus 1. Okay. Anyway, look, these are all just standard things, so you should know these. So this ends up being, I always tell my undergrads, not that I'm going to put this on a key or anything. When you get confused about a proof, like what remember I did right here, ln A plus ln B is equal to ln A times B. If I'm like not sure about that, I just get a calculator and I ln 3 plus ln 5. I always use odd numbers. Anyway, that's just how I make sure that I'm not like all whacked out when it comes to trying to remember a little math identity that I need. Okay, in this case, ln A plus ln B is ln AB. That is true. The minus sign just gets taken up into the argument of the exponential. So there you go. Okay, so remember I'm still Legendre transforming. I'm still working with entropy, just a Legendre transform of it. And now I've got it into this form here. Okay, so what? I'm actually almost done. Now remember that this is Q. This is technically what Q is. This is not useful yet. Let me point out what I do with this. Number of microstates. Okay, another neat trick. Let's say the number of microstates is 3. 3 holes and 1 X on it, like I've been doing, one chess piece on a chessboard. The number of microstates is 3. What I could do is take something and add it 3 times. In other words, I can take the number of microstates and I can multiply the number of microstates times this number by simply summing this thing W times. See what I mean? Right, so if this is 1,000, I can actually replace this with a summation from 1 to 1,000 of whatever, of anything, of the number 1. Then it turns into 1,000. Well, there you go. It doesn't have to be the number 1. It can be this. I to the number of states. Again, I know this is kind of funky, but this is what I'm doing. Again, if the number of states is 1,000, I could either say 1,000 times this number, or I could add this number 1,000 times, and it's the same damn thing. So that's what I choose to do. Therefore, this is equal to ln sum of states, e to the minus beta. Now, if I'm going to sum up states, I have to keep track of states, and for that I will put a little u sub I. Not all states would have necessarily the same internal energy. Maybe they do, maybe they don't. In this case, they wouldn't. No, someone wouldn't know that later. Okay, and again, this is Q. Okay. So let me. I'll leave that up there. Let me write this down again. Let me write the start of the derivation to the end of the derivation. Okay, S over KB minus beta U, again this is entropy, different form of entropy, is minus beta A is natural log of the sum of states e to the minus beta U sub I. Okay. This one is dead, so I'll get rid of it. One more. Okay, so what's the point of this? It turns out that there are plenty of model systems for which I can know the number of states and their internal energy. The quantum vibration, right? I know what those energies are. I know their degeneracies. I know everything about them, right? So here's the point. If I have a certain model system where I know all the states and I know their energies, and again, in quantum, there are, and we know so much via quantum mechanics. Rotational states, vibrational states, just about anything. Electronic states, I know what they are. I know their energies. I have this information, and now I've got their free energy too. And this is a hell of a useful thing. Let me explain a little bit more about A. By the way, so let me just give you the last thing you need to know. Oh no, Q is called a canonical dead pen. Okay, canonical partition function. Literally about one of the most important things in physical chemistry, the canonical partition function. And this is what it is. Again, the importance is that it gives me an easy way to calculate free energy of stuff, anything. And again, so a large part of what we're going to do for the remainder of the semester is look at model systems, which I easily know this, and I'll get the free energy. I know it's not G, but A is as good as G as long as the gas isn't created or destroyed, which is a fairly large number of things. Okay, now let me tell you something that really bothered me when I was a grad student, an undergrad as well. What is the difference between U and A, or H and G? Why, now we call A and G, we call those free energies. Why are they so important that they get an extra name that U and H don't? Now for one, they're natural variables A and G. Let's forget G, right, for all the reasons I said. A is free energy. It's more important than U, way more important. And it's because its natural variable is T. U, natural variable is S. A, natural variable T. For this distinction, A gets to be called free energy. A is much more important than U. It gets that name. Now look in Atkins P-Chem, and it says, what is free energy? Free energy is all the energy available to us, all the energy available in a system. So what? That is like, life should be lived. I mean, I have no idea what that means, right? That's the NSF. Anyway, when I see, platitudes like this, free energy is all the energy available to a system or from a system, and I'm actually blanking out on that. I don't know what that means. I do now. It's just, and it's not really all that complicated. It's just not explained that well. I'm going to try to put that in my textbook. Did I ever mention that? Kitties. Anyway, okay, so what does that mean? What does free energy mean? What does it mean to have all available energy from a system, and how is it different than U? Okay, now this is helpful if any of you have ever done any molecular dynamics simulations. MD simulations are reliant upon stat mech, and so I'm going to frequently invoke a picture of, say, molecules in a simulation box, and you can visualize this. This isn't hard. Okay, now let's work in a world of U versus A being free energy, being more important than U. What does it mean that A is all the energy available from a system? Okay, well that means I'm going to suck all the energy out. Now let's say that the system is composed of a bunch of water molecules, and they're at room temperature. They're moving around. Okay, great. They're moving around. Now note that if I'm going to remove all the energy, let me remind you that delta S total has to be greater than 0. So, in this process of removing energy out of the system, fine, I have to keep the total entropy has to increase for me to do so. Because for me to remove the energy from anything requires a total increase in entropy. It requires an increase in total entropy. Because everything requires a total increase in entropy. Every single thing that's ever happened ever requires that. Same's true here. Water, same model of water. Again, remind you that I have a magic vacuum, an energy vacuum that's going to suck the energy out. This guy is more important than this guy. Why? Now again, total entropy has to increase. But in a world of U, for this to be true, system entropy is 0. Recall? For total entropy to increase, in a world of U, the system entropy can't change. There's someone knocking at the door. Let's let him in and just see what happens. No, go ahead, let him in. They're knocking on the door. No, open the door. Open. I just want to see what they'll do. Nothing?
It was already open.
No, okay.
They knocked
on the door. I was just curious. Anyway, okay. So sorry, I just got confused who they were. I thought that someone was late and the door was locked. Anyway, okay. So again, if I'm going to suck all the energy out with the magic energy vacuum, the configuration, the jumble of molecules can't really change that much because it has to keep its system entropy constant. Because remember that in a world of U, we can only have a total entropy increase. A stipulation is that the system entropy has to be 0. Change in system entropy has to be 0. Okay, now in a world of A, that's not true. So when I suck all the energy out of this thing, it still has to be very jumbled looking. And so I don't know how much energy I can get out of that. But in this guy, where delta S is allowed to be negative, I can suck all the energy out in such a way as to leave a perfect crystal. I'm allowed to do that. And that would have no entropy, right? Right, so again, if I'm going to suck all the energy out, I'm going to get more out of this one. Because in this one, I can pull so much energy out that the damn thing crystallizes. Whereas I can't do that with this one because that would violate the total system entropy has to be 0. I can't crystallize it in that case. I can't crystallize this and have that true. So you can imagine that there's more available energy here than in here for this reason. Because I can get left with a perfect crystal, which you can imagine, it takes energy to jumble. And so therefore I can take energy out, more energy out. You kind of see that? It's a little funky, but this is just why A and G are special and U and H are not. It has to do with their natural dependence and it has to do with the fact that I can suck more energy out. This truly represents all the energy available to a system. That's why that difference exists. Okay, anyway. Last bit, I'll show you one more proof and we'll stop there, and then next time I'm going to show you something really cool. But God knows I've not been a little off today, for all the reasons I said. Let me show you a neat little proof. And I just won't have time to show you the other neat proof, so that's a little unfortunate because I kind of ran my mouth today. Let's see what else. Oh, yeah, this is kind of neat. So remember the Boltzmann equation. Not the Boltzmann formula, Boltzmann equation. I told you that Q is important for more than one reason. Boltzmann formula is KLNW, KBLNW for entropy. Boltzmann equation tells you the probability of a state. The probability of anything, really. Probability of anything with energy. This is the proper probability distribution formula for energy, as nature defines it. So the probability of a state, the state would have an internal energy U sub I. Now, for all the reasons I just mentioned, we better divide by kBT. I should be just saying beta U, but just, again, I'll go easy on you. Divided by all possibilities. Yeah, what's wrong with me? Okay. Look familiar? Have you folks seen this before? You should have seen this in your derivation of Maxwell-Boltzmann distributions. Remember velocity distributions of gases, which is typically done in PChem2? This was actually your starting point. And from this, if you plug in internal energy, if you make that kinetic energy 1/2 mv squared, then you derive the Maxwell-Boltzmann distribution for velocities of the gas. This was your starting point. This is nature's probability distribution for energy. This is how much energy nature distributes based on probability. It just is, right? This actually can be derived. It takes about a day, but I could show you how to do that. Now you notice something? Now let me get back into that. What's this? Q? Yes, it's Q. There we go. There's your canonical partition function. It actually appears in a whole bunch of stuff, by the way. Now let me just show you one thing that's kind of neat. Okay. Now notice again, I'm working with the canonical partition function. Now that automatically means that I'm working in a world of constant volume and constant internal energy. Now again, for this to appear, at some point I took entropy and I subtracted out its dependence on internal energy and put it on temperature. I am working in a world of temperature and volume. Now, that is not U's world. U is not constant in this world. U is the buddy of entropy, but I'm not in entropy land. I'm in entropy's Legendre transform land. That is not the land of U. It's the land of A. Now, because I'm not in the land of U, U is allowed to vary. Right? Entropy can vary, so can U. But I'm not in entropy's land. I'm in entropy Legendre transform land. So entropy can vary, and so can U. So that's why I'm saying I need to calculate the average. To do that, as can work with absolutely anything, take the possibilities times the probability of that possibility. This is true of absolutely everything, right? Okay. Now I've defined the probability as above. E1 minus beta U over Q. Okay. Now, okay, so what? Now, right now, by the way, these are just standard calculus definitions. With the Boltzmann formula. If you have a formula for probability, again, this is true for anything. I happen to pick internal energy. But let me point this out. And I see I'm over time. I'll be quick. The derivative of natural log x is 1 over x. Therefore, the derivative of natural log of the canonical partition function with respect to beta is 1 over q Now be careful. Now this is where you got to be a little bit better at math. If you're a physical chemist, you should always know that there can be other betas hidden in Q. Now the reason that this is, if I look at the formula for Q, I see a beta here, but now here's the damnedest thing. Now this is where this is kind of jarring in all honesty. I haven't really told you what U is. U for what? Sum of states. What states? Cat states? Donkey states? Monkey states? I don't know what is in this U. You're not allowed to assume that there's no betas hiding inside of it. So while the natural log of x is 1 over x, if there's an x inside the x, you have to do another derivation. Remember, this is the, what do you call this? Product rule. This is the product rule of calculus. Okay, now what's this? dq to beta is the derivative of beta to the sum of e to the minus beta u, which ends up being minus the sum of states. Okay, e to the something times x, derivative with respect to x, is that something times the original function. Okay. Okay, again, see that? Now, let me go back here. Derivative of the natural log is 1 over that function, but I'm telling you that there can be betas still inside the Q, and in fact there are. So when I take that derivative, here's my definition of Q. I do the derivative of, with respect to beta, I made a mistake. Then I bring down the thing that multiplies with u sub I. Okay, sorry, I put down beta, but I should put u sub I. Okay. So therefore, let me erase myself because I'm over time and I don't want to keep you. U sub I e to the minus beta u sub I. Now you see what I've done? This over Q is the probability of the state. Sorry, I'm using the word bad, which is of course the average internal energy. Okay. So to summarize what we've gotten so far. Now remember, I want to emphasize quite strongly, there are a huge number of real chemical systems for which I can know the total number of states and their internal energy. And from that, I see that I've already gotten a whole bunch of stuff. I can see that natural log of that canonical partition function is minus beta A. Is that right? Minus beta A. And I can take the derivative of the canonical partition function with respect to beta, we'll minus that, and now I can get the average internal energy. Now remember, I explained why not the average A? Because in the world of Q is a constant volume, constant temperature. A is constant volume, constant temperature. That means it's well defined. There, I don't need to write average. U is not well defined, so it can fluctuate. So that's why this guy gets an average and this guy doesn't. Anyway, Q can be very well defined, and now you see, you notice how I'm picking out thermodynamic parameters? I can do this all day. I can calculate any thermodynamic parameter necessary from Q. I've just done 2 of them. I can do more. In fact, I will. I'll start picking more model systems next time. Now, let me show you what we're going to do next time, because I know this is kind of a little boring, but let me tell you what I'm going to do next time, and this is really fascinating. What we're going to do is this. Now, this is the definition of a variance. This is the variance in internal energy. So let's think about a box of water, okay, in a molecular dynamics simulation. The waters are moving around. You know, we have some software. We drew a model. We said, go software. The water starts moving around, and we do that at constant volume and constant temperature. And we can calculate the internal energy. And it's fluctuating. This is the variance. This is the variance in the internal energy. So what? Next time, that's the heat capacity. So what? If energy did not fluctuate dynamically in a system, there would be no heat capacity. Heat capacity, which is really freaking important, if the heat capacity of the universe was 0, we'd all explode immediately at the speed of light. That's true. That keeps us from exploding at the speed of light, so no heat capacity. But it only exists because when molecules interact, they dynamically change their energy. The way they interact with each other causes this fluctuation in their internal energy that allows heat capacity to exist and keeps us from exploding at the speed of light. So, good job. Anyway, this is one of the kinds of relationships that I can derive with StatMech that you cannot derive by any other means. So I'm going to do this next time, and I'll complain some more, because I like doing that.